We're now moving on to the topic of AdS₃ quantum gravity. And what I was proposing for you to do was to do a first attempt at computing this path integral as a sum over metrics with a big fixed boundary condition weighted by their appropriate action. And I guess here I was using 3D for the appropriate action. In this case, it will be the Einstein-Hilbert action plus the Gibbons-Hawking-York term and plus the counter term that we had before. Okay, so we're going to try to do that computation. And the way that we're going to think about this computation was that a reasonable thing to think is that this path integral, so I write exclamation point because it's an assumption that we're using and how to define and basically what it means to do this integral. And the working assumption of Maloney and Witten is that this path integral should be organized in terms of a saddle point approximation, where these are solutions to the equations of motion. And basically, you will compute the contribution to each of those equations of motions where the set of G0 is going to have basically a tree-level contribution, a one-loop contribution. So here I was pulling out factors of C to make this clear. But basically, this is the loop expansion around each saddle. Okay? So this is what we're just going to see what, if given this big assumption here, let's see what that gives, that computation gives. Okay? We're just explorers at this point. Okay? We're just going to brave and do that computation and see if it gives something simple. Reasonable. Okay, so one thing that is that now I want to, as we do this, the first thing like we should focus on is basically on this part here. So we have a sum over these solutions, and this basically means that you're summing over all, in particular, it will mean that I will sum over all topologies that comply with the boundary condition. And at the moment, the boundary condition that I chose was that the boundary metric was a torus. And there's going to be another input that we'll talk about as we move along. But for now, I'm also going to consider all smooth geometries, smooth, and I should say also real Euclidean geometries. And finally, it's already in the definition, but I just want to stress as well that they solve the equations of motions, i.e. they're Einstein manifolds in this case. Okay, so what is one solution that complies with this boundary condition? Right, so thermal AdS₃, just to be precise, because we want the Euclidean version and we want it to have, what's very important is that we're fixing basically the torus at the boundary, right? So one solution that obeys the three criteria, or I should say one manifold, just to be, since one of the criteria is that it's a solution. So one manifold that obeys the three criteria is thermal AdS₃. And let's just write down for completeness the metric again, just so we're all clear. I guess I was calling this guy capital T. Like this. So this is the metric of thermal AdS₃, where if you define omega as phi plus ITE, omega will obey my boundary conditions, provided, like, that's the key part that tells me that it's within the class. Well, these two things combined is what tells me that this will have the property that it's a manifold where the boundary is a torus with complex structure tau. Okay? Yeah. Yeah. I'm just, let me try this first. Okay? So let me maybe be explicit. So basically, I'm assuming that some reasonable set of rules is that they should be, basically, I should be considering all possible topologies. I should be considering things that are smooth and things that solve the equations of motions, okay? Again, as you guys all know, path integrals are very kind of like subtle things. Even in QFT, people will tell you like, oh, it's just some symbol, and then depending on the theory is how you define that symbol. And so in gravity, the symbol is not very clear. And so here I'm just suggesting for you some rules which seem okay. Like, it's a good starting point, okay? And the nice thing, again, in 3D gravity is that I have imposing this set of rules is something that I have control over because you can quantify everything given those rules, okay? Good, so.
How would you know if your assumptions are not exactly right and which ones you need to modify? Like what's going to be pinpointing that there's something wrong?
Yeah, so what would be a successful outcome, basically?
Well, that we have a trace interpretation of this. But
and so if we don't, then we'll go back to, so if we don't, then we'll have to revisit, you will have to revisit these assumptions. You might have to revisit the fact that it admitted a saddle point approximation. Like, there's all sorts of, yeah. So if we don't succeed, like, what gives? And that's not. We want the trace interpretation. We want to understand, yeah, how do you go from a gravitational path integral to a trace? So what is it, when do path integrals over metrics allow a trace interpretation. That means that you understood what quantum gravity is. Otherwise, it's not quantum gravity, it's just something that you computed that doesn't look, well, okay, you can say, okay, people debate on like what quantum means, but okay, for me, my working assumption is that being successful at quantum gravity means that I managed to evaluate that path integral and obtain a trace over a Hilbert space. And I have control on what that Hilbert space is.
I have another question that I think is maybe an extra assumption. Is that if I know that this is Euclidean signature, but if I think in terms of real-time formalism for thermal physics, I could imagine saying I need to demand that those smooth Euclidean geometries, I can use them for prepared state, and when they evolve Lorentzially, I need to make sure that there is not any weird causal problem. Like
that's too strong. If I do that, it's you can impose it.
But that then, if I consider those, like say, but that will against the philosophy of real-time formalism, right? That is. I mean,
which I'm not using, right now I'm trying to just say what would be the rules in Euclidean signature, and hopefully if I get a trace, it will tell me that I have good rules in Lorentzian signature. Let me put it that way, because if I manage to cast this as a trace of e to the minus beta h, it means that there's a good Hamiltonian that evolves the system. And then you can say like, oh, what are the states on which this thing is acting, and giving you like some nice like evolution, but I don't want to, like, you could start there, but I think I'm going, like, I don't want to. So you do it, you write that paper.
But the point is like all of this geometry, if I continue to Lorentzian
all of this geometry, I just written one.
Yeah, the other one that you will write down will have a good causal structure in Lorentzian signature?
No.
Right.
Okay. So good. So this is one solution that has all these three properties. So now what are other solutions? Or other manifolds? Obeying this criteria. So we know of one other one, right? What would be the other manifold that obeys this criteria? Right, like the simple version, so you would have said, oh, the Euclidean BT set, for which the only thing that you have to do is take tau to minus 1 over tau. Okay, so that will obey the same criteria, so this is another one. So we have here 1, 2. But there's actually a whole family of other solutions. So you don't just have to take tau to minus 1 over tau. Any manifold, so if you start with this one, and you do this transformation, where where A, B, C, D belong to SL2 set. So you would just do the diffeomorphism that changes the complex structure to this. I invite you to figure out what is that diffeomorphism. It's not difficult to work out. But basically, or put it in a different way, if you write basically this geometry, but instead of putting tau, you put any of these combinations, it's still the same torus with the same complex structure. And this basically tells you that I actually have, since A, B, C, and D run through the integers, I have an infinite family of basically Euclidean geometries that obey the boundary conditions. So there's an infinite of Euclidean geometries. With the property that DM is a torus with a given complex structure. Okay? So from the point of view now of writing this, what will happen is that I will have basically the contribution. Let's say that I start by looking at what is the contribution from what I'm going to call, I'll call it the thermal AdS contribution. Okay, so let's say that you start with this one that will depend on tau and tau bar. So you will compute the contribution of this geometry. Then you would tell me like, oh, add up the one that comes from BT-set. But now the one that comes from BT-set is basically whatever you get in thermal AdS, but just change, instead of writing tau and tau bar, just write -1 over tau bar and so forth for all of them. And so this thing basically just becomes a sum. So here gamma is basically an element of SL2 set. Of whatever you have for thermal AdS. Sorry. It's a sum of that type. Okay? So this is my sum. Over topologies. Okay? Or over the different classical solutions if you want. And you can convince yourself, I'm not going to prove it, but you can convince yourself that with this boundary condition, with this boundary conditions, these are the only manifolds that comply with the 3 criteria. There's no other solutions. There's no other smooth manifolds that will comply with these 3 criteria. Yes, there's a question there. Because these ones, it's related to what Robinson was asking. If you continue them to Lorentzian signature, they're complex. So that's why the Euclidean BT set was special. So these other ones, they're called the SL2 set family of BT set solutions. But if you wick rotate them back, they will look complex. There's a question in the back. So now let's specify, I have to specify what this is. So, but I'm not summing, no, so if you're thinking of this picture, yeah, I'm basically, I need to specify to you which region I'm summing over. So, yeah. Oh, well, basically I'll put it, so here the gamma, I'm not going to be doing an integral over tau, just to be clear. So tau is something that is fixed. I just have to specify what is exactly the ranges of A, B, C, and D that I'm going to be summing over. Yeah, it will be related to it. It's basically where are you kind of putting, like, so you make representatives of that. But the sum is over the values, so that's why I was stressing it's a sum over the elements of SL2 set. But this is not like if you're familiar with string theory, you will like integrate over the complex structure. That's not what I'm doing because the path integral is a function of the complex structure. Yeah. And so, good. So we have that, but now let's be a bit careful on what is the range here. So one thing that you have to be careful about is that there's one element here. So one thing to note is that the element that looks like 1n, 0, 1, so the element of SL2 set, so this is clearly one of the representatives of SL2 set. This is what you will call a T transformation. or T to the N. So this transformation, what it does, it takes the complex structure to tau plus n, with n an integer. So it's just shifting by an integer the complex structure, which of course, and from this point of view, you can see that that's a symmetry that you can do because it's just kind of mixing these two periodicities. But it doesn't do anything. So under this transformation, so under T to the N, C thermal of this gamma, of this very specific gamma, it doesn't change. You can view it from the point of view of like if you compute the on-shell action and you shift tau by n, like it doesn't do anything. Okay, so if you go back, like when for instance, that's a simple way how to see it. Like if you go back and compute the on-shell action with some tau that differs by n, like the on-shell action is the same. Okay, so this is one of the elements of SL2 set that actually didn't give you anything. And so the thing that you're summing over here, it's basically a restricted group. And so the sum, so let me write it here. So removing this, basically the answer is that you need to sum over C's and D's that are co-prime, and C has to be an integer bigger than 0, sorry. And then you will have the answer of thermal AdS, and then you will write it like this, just to be explicit. Plus D, okay? So that's the sum that you have to do. Yeah, you just, it's the one that has basically A equal to 0, and then B and C are 1 and minus 1. And D equal to 0. So S, this one. Oh, I'm just generalizing it. I'm just saying, it was just kind of like, it's just because we saw this one in lecture, so this one you're already familiar. And then I'm just saying like, oh, there's actually a whole family of them. So this includes everything.
What would be the difference between a preemptive set and whatever other tau that isn't that also bit set?
No, so that's what I was saying. If you go to Lorentzian signature, the geometry is going to look complex. Yeah. Okay. Okay. No. They act on the same. Yeah. No. So there's not like a. Of course, you can try to do it. You can put here like a gamma 1 and a gamma 2, but that's not going to give you something smooth. So these are the you act with the same gamma on both tau and tau bar. That will give you the same torus. If you do things like really separately, then it kind of looks like, will look weird. Yeah. Oh, okay, yes. Do you want me to rewrite this equation? Yes, okay. Okay. Good.
Sorry, why do you call as sum over the topology when you are saying that it's solving?
Well, sum over different manifolds. That's all. I call it topologies if you want. Yeah, because we know that this solution is kind of distinct from this solution. That's all. From the Lorentzian point of view, that's all. You're considering in principle things. I know from you, they're all solid tori, but yeah, get over it. But yeah, it's more from a Lorentzian point of view that you would say these are distinct, like manifolds. They also, from the Euclidean point of view, we also saw that there were different ones. But yes, they're all topologically solid torus, but okay. In general, it's mostly because if you change the boundary conditions and you do something more more complicated, there will be a sum over topology. So I just want you to think about this sum over the different G0s as basically including the possibility of having different topologies. But my boundary condition is quite simple, and it's basically just changing the complex structure of the solution. Okay, now mathematically, this type of sums have a name. For those of you that are more mathematically inclined, and this is called a Poincaré series. Okay, so that's the sum that we have to do. But now the thing that next we have to do, like before we can actually do the sum, we need to know what this function is in here, or not yet. That they're co-prime. Yeah, that's C comma D equal to 1 means that they're co-prime. Okay, so let's compute. So now we need to evaluate this contribution. So we need to know what this function is, okay? And this is the function that is going to include all of these little loop corrections, okay? So there's a few ways, there's at least 2 ways to proceed.
Excuse me? I'm a little bit ashamed, but what does it mean to be co-prime?
Later. Or someone else. Can someone tell her what does it mean to be co-prime? Nobody? No, she wants a definition of what co-prime is, not what. Okay. Very good. So there's 2 ways that you can do this computation, and there's papers that have done it in these 2 different ways. One is doing it, so you can do it in a Euclidean approach. And by a Euclidean approach, what you would do, you would say, okay, so I had this big path integral that was an integral over metrics, weighted by their action. And you would say, okay, let me write G as G0, where this G0 will be thermal AdS, and then plus a fluctuation, plus something quantum. And what you would do then is just expand out the action. So you would say, what is G around G0 plus H? So you start doing perturbation theory basically means, that loop expansion basically means that you're treating H as a perturbative quantity. And so then you would get here the first contribution as an expansion in H. You get the action evaluated on the solution. Then you will get the first variation of the action with respect to the metric evaluated at G0 times h, then you would get a second variation of the action with respect to the metric evaluated at G0 times h squared, and so forth. Okay? This is what it means to do, basically, perturbation theory, like the loop expansion in quantum field theory, right? Now, so this is the on-shell action. That we know. What about this? No, 0, because it's evaluated in a solution. It's a variation. So this will be just 0. This will already contain the contribution of the stress tensor, just in case. So this part is going to be 0. And this, for instance, the first non-trivial term that you get is going to be a one-loop determinant. So this is your one-loop contribution. If you keep on going higher powers in h, you're going to get more and more loop orders, okay? So higher powers in h is more gravitons that you're exchanging and as you go higher up, okay? Now, why is it called a determinant? It's called a determinant because basically, let's replace that expansion in there. So this will mean that I will get S. Oh, sorry, I was supposed to write bigger. So if I replace this expansion in the path integral, it will tell me that now I'm integrating over h, okay? And what I get in the effective action here, schematically, there's integrals and stuff, but please, like, I'm not going to keep track. There's also indices, so I'm being very kind of schematic in, like, not keeping track of the indices. So I hope that's also okay. But this basically looks like a second order. So this will be a second variation of the metric. This is going to basically look like something that will be well, it won't matter too much. Okay, so there's some second variation of the action times h squared schematically. And then, okay, there's more corrections. But if you truncate it up to here, this integral is a Gaussian. And so basically, this integral is a determinant of whatever operator you have up there, well, the inverse of that operator. And depending on factors, if you normalize this by 1/2, it will be like -1/2. If you have ghost, so at this stage, you also have to take care of, like, when you do this expansion, when you expand out h, you have to make a choice of gauge. And so then here you're also going to have to divide by the volume of whatever you gauge fixed. So there will be also ratios of determinants. You also get ghost determinants and so forth. But this is basically what I want to illustrate, is that this first correction is a one-loop determinant of the Euclidean path integral. Okay? And in 3D gravity, even though you don't have gravitons per se, this is still something that you can do. And it works as in any other number of dimensions. Okay? It's actually it's very pretty. So if you wanted to see the details of this computation, a very nice paper, there's several, but one that does it in, like, the most traditional QFT way is Yombi, Maloney, and Yin. And you can see there how they actually go about doing that expansion, doing gauge fixing, and then computing those determinants quite explicitly, okay? Up to one loop. So that's something that you can do. That's one way that you can compute it. Another way that you can compute it that maybe it might be a bit more sort of controversial in a sense, or less intuitive, like you would say, like, oh, there's a lot of assumptions now here. There's also a Lorentzian way how to do it. In the way of saying, look, we understood what the phase space of AdS₃, like what were all possible, what was the phase space around thermal AdS₃. We got that the phase space was described by 2 copies of the Virasoro algebra. So then just basically, so from here you would use just the notion, the understanding that you have about the classical phase space. Which is basically 2 copies of Virasoro. And you would say quantize that. And you know what the quantum version, you know what the Hilbert space associated to 2 copies of Virasoro is. So this was the way that was done. If you read in the Maloney-Witten paper that set up this part of the computation, they do it that way, okay? They basically work under the assumption that whatever you're computing here should give you, should be compatible with the fact that the phase space was 2 copies of Virasoro. Now, the beautiful thing is that these 2 methods agree. They will give you the same answer, so I'm just going to tell you what the answer is. So this is the answer that you would get for that contribution of the path integral, where eta of tau is the eta Dedekind function. I guess many of you don't know what the eta Dedekind function is. No, you don't know what the eta Dedekind function is. Okay, so I'll write this. You can infer, well, let's see if I remember the definition of the eta Dedekind function. That's the eta Dedekind function. I hope I got it correct. It looks correct, morally. So it's a product. One way how to write it is that it's a product of 1 minus q to the n with this funny factor of q to the 1 over 24. And the way that you understand this answer, and that's why it connects very well with the Lorentzian method, is that what this function is counting, so this answer here has an interpretation as a trace over some small Hilbert space of what we will call q to the L0 and q bar to the L0 bar, where what you're counting here, so this is kind of a nice function. It's going to be a discrete series in Q. But what this thing is counting is basically it's counting states where what you did, or sorry, let me write this. I was writing them as the calligraphic L0s. So these are the Virasoro generators, the zero modes of the Virasoro generator. And you're basically counting states that basically are Ln negative, acting on a vacuum state, where this vacuum state will be basically AdS₃. And the same thing, you can also put L bars with different integers. So you're basically counting all the possible ways that you can act with the L's here. And this is what's called a highest weight representation of this Virasoro algebra. Okay? So it counts the descendants. If you're familiar with CFT, you're basically counting the descendants of the vacuum state. And it's a vacuum state, so if in the jargon of CFT, if this was a primary, you would just get this. The reason why I add these two things here, so maybe let me comment on some pieces here. These pieces here are coming because the vacuum state is annihilated by L minus 1. So you have to remove some of the counting from this. This part here, these parts that come with C, this is your tree level action. So from the point of view of the path integral, this powers of minus C over 24. And that's what we wrote for thermal AdS. Do you remember? The action was like C times tau. I just packaged them as a function of this little q, but it's the same thing. That was a tree level action. The shift by minus 1 over 24 is because I put the eta here that has this pesky thing of q to the 1 over 24. That's all. It's because I decided to write it as a function of eta. But then basically, this what I get as a function, what this mini like path integral is doing is counting all the descendants that I got from my phase space. Okay. Yeah. So when you do this, but that's already taken into account. Yeah. So that's what it will mean to promote this classical phase space to a quantum one. So you would have to implement. Well, it's already so. The operators have commutation relationships. They're not local operators. So if you write them as local operators, you have to normal order them. But these are already like the Fourier modes of that. So just think of it as like you have an algebra, and you're looking at representations of that algebra. Okay? If you write down like the local stress tensor and you compute a 2-point function of it, then you have to tell me like, what is your prescription for normal ordering? But these things don't depend on X. But yeah, if you want also here, like if you think of them in terms of creation and annihilation operators, there's a rule of like, oh, you first all put the A daggers and then the A's. But like these states are going to be annihilated. So the rule, if you want, and that comes with normal ordering, is that L with a positive n annihilates the vacuum. So these highest weight representations are defined by the fact that Ln acting on 0 is 0 when n is bigger than 0. So that's a defining, and the same thing for the bar. And so then if you have a prescription of like, you put all the creation operators first, or like, well, I forget, like, okay, you have a rule of like, how do you put creation and destruction operators? That's your prescription of normal ordering. That comes implicitly in the construction of the states. Yeah, but it kind of comes for free. Like you don't have to If you're a mathematician, this like it's just representation theory of some given algebra, if you want. In physics, we call it like, we give it different names, but yeah. But in any case, the nice thing is that if you do this Euclidean path integral, you would get exactly the same function, and then you would reinterpret it as like, oh, I'm counting those states. So this part of the path integral has a nice discrete interpretation in terms of a trace, which is really nice, right? So now we're kind of optimistic of like, maybe we'll get something reasonable out of this computation. If you want another way how to say what happens here, is that the conclusion of this little part is that, intermediate conclusion is that doing quantum field theory on a fixed G0, so that's what we're doing at this step, because we're just grabbing a fixed G0 and then looking at perturbative contributions around it, does have a good Hilbert space interpretation. Okay. That you can interpret it as a trace. So if you expand this thing in Q, you will have discrete powers of Q throughout. What's that? I don't know. Okay. Okay.
That result, if I look over to the Euclidean version of the computation, where do the Q's come from? From the path integral or from the
The G0. The G0 depends on tau.
okay. 1 minus Q and 1 minus Q bar are the parts from the path integral? What's
The part that comes from the part that depends on C is what you got from tree level. Everything else is what you got from doing that one loop determinant. So strip off this Q to the C over 24 and Q bar to the C over 24. Everything else came from that one loop determinant. Yeah. Now, you might worry that there should have been higher loop corrections. And this is something, it's funny. So from this approach, so naively, so another note here. So the one loop correction already gave me that, but you might ask yourself, what about higher loops? And from the Euclidean point of view, you should in principle keep on doing higher loop corrections. But this is where theorists are a little bit lazy. And the thing is that given that it matched this computation, or well, given that it already gave you something that was compatible with the representations of the Virasoro group, it is known that quantization of, so these representations come from quantizing diff S1. And there are arguments, or well, even from a point of view of a CFT, or however you want to understand it, the quantization of this is one loop exact. And so the folklore is that if you kept on doing higher loop corrections here, you should see that they're basically trivial, that the only thing that they will do is renormalize the value of the central charge, but they will not change the ADAP part. Like, you're not going to get anything interesting. So the only thing that higher loops can do is renormalize C. So what you meant by that number there. So the punchline is basically that this, sorry, I have way too many equations here. Let me start erasing. Oh no, actually I'm not going to erase that because those were my assumptions. No, it doesn't. Well, a leading order, it's going to be the Brown-Hainaut central charge, but it could get renormalized. You can get like, yeah, like corrections in G, like order 1 corrections. And that's also known, like we know that, yeah, 3L over 2G is just the leading order answer. But so in some sense, but it doesn't, like from what I'm going to say, that doesn't matter. You can just write down here there's some C effective or some C renormalized. So how it depends on G Newton is not going to be like super important at this stage of the conversation. It's how many powers of H's you have, yeah. I integrate it over the H's. So it's a path integral. You do an integral over all the possible ways that you can exchange gravitons. So the final answer is just a function of tau and tau bar, as like the definition, like you're summing over everything that could happen. So the final answer is this, but yeah. So I did that. Like that's what you're doing here. You're integrating over all the values of H's, but then because it goes like e to the minus h squared, it's like a Gaussian integral that you're doing. No, the action will tell you. You just have to vary this action with respect to the metric up to second order.
Yeah, and that will give you some contractions of H with itself. That schematically.
This thing here is going to be a tensor that has 4 components. So if you want, and this as a tensor, it might have things that contract the H's. It also can have derivatives. It will have like different things. Yeah, because morally it's like 2 powers of H, right? Just click. So what you do here, formally what you do here is that you have some differential operator. So this thing looks like H times a differential operator times H. So it's like a Laplace type equation. And then you just say, what are the eigenvalues of this operator? So you construct eigenvectors to this operator, and that's why then it just looks like a Gaussian. So you basically construct it's just that. You construct the eigenstates of whatever shows up here, and then this determinant is the multiplication of these eigenvalues. So that's why it's called a determinant, because it's like these eigenvalues. Like, yeah, so for each eigenvector, you'll have a Gaussian that will give you 1 over square root of lambda, and then off you go. Okay. Where was I? Yeah. So at this, sorry, I said I don't want to erase the assumptions because I'll come back to them. So the conclusion for now, oh sorry, I put it over there. So the conclusion that now is that, sorry, let me just write it here then. So is that it was good to do this, and that on this boundary condition is one loop exact. Okay, great. So we have basically, now we have all the information needed to compute this thing. So I had it written up there. So now we will have the sum over C and D being co-prime. And you will input that horrendous expression there, so you will have 1 over eta of the appropriate gamma acting on this. So these are now all explicit functions. Yeah, let me. Here, I'm just going to be putting acting on gamma because the tau now here is inside of the Q, and I don't want to write too much. But now this is an explicit sum. Okay, so there's some explicit functions here, and I just have to do this sum. It's a nasty sum, but actually, so the thing that Maloney and Witten did is that they actually computed it. And what they got is the following. So they got the answer that you get for thermal AdS as a function of tau and tau bar. And then, so you know that that's going to be like the first contribution from here, so that's not surprising. And the answer there, so you have to regulate it. This is still like the difficulty, and that's why it takes a while if I tell you in details like how you do this sum. It's there is a lot of math that goes into it because the range of the sum is infinite, and so you have to regulate. It's actually not a convergent sum, so you have to do some regularization of it. And so they did like if I remember correctly, I think it was a Seda function type regularization of the sum. And then there's some coefficients here. And they wrote it like this. So there's some very nasty expansion of this function. And here y is the imaginary part of tau. But they basically get a finite answer. And this is, there's a whole series here. I'm just illustrating what the first few terms are in this sum. And this is what they get. No? No. Sorry, C here has nothing. Sorry, this is the central charge, and this is an integer. Sorry, I am abusing notation. So let me write this one with red. Yeah, that C has nothing to do with that C. So yeah, this was the element of SL2 set. This one here is 3L over 2G if you want, or whatever. Like it's your coupling. What's that? Yeah, it's fixed. It's basically your coupling constant in the theory. No. It's fixed by the action. So it's the strength. It's the AdS radius divided by G Newton. So the action will tell you what is my coupling constant. Yeah. So it's like H bar if you want. Like, but yeah, it's a coupling constant. Yeah, if you want the third parameter, I'm writing it as like. Yeah, what theory you're computing the path integral for. So this is the geometric data that I'm fixing, and this piece is implicitly telling me what is the theory that I have, and that's encoded in the coupling constant that I get. Yeah, but we usually, when we write path integrals, okay, it depends on what you're doing. Sometimes you don't put explicitly that there's dependence on couplings when you write it as a function, if you see what I mean. Like, of course, I could have written like, oh, this was a function of G Newton, L AdS, and tau bar, but it's like a bit pedant, like, yeah, okay. But of course, yes, path integrals will depend on the couplings that there are, and that C is the coupling. There has nothing to do with the C. But thank you for that. Like, it's just that yeah, you don't want to, yeah. C is the natural thing in SL2 set, but then C is also the natural thing to call a central charge, and so then you don't want to change too much the notation. Yeah. What's that? Oh, I'm just writing it as an expansion, so you can decide, like, yeah, so it doesn't have to necessarily be big, but basically what they were trying to do, so you just get like some function, you get something, and you're trying to like understand, so there's like some Bessel functions in there and like some nasty stuff, and you're just trying to understand like what's inside of this function. So here, I just wrote down for you, like, what do you get as an expansion and why? This is not expanded, like, so you remove, like, you keep one part, which is the part, like the first contribution, and then the rest you kind of expand in y. But of course, there's still y dependence in the eta, so I'm just trying to illustrate a bit, like, what we get. So this is what you get. And again, you can write a more closed form expression in terms of some horrendous functions. You can look at them in the paper. But this is roughly speaking, this is all I need for the lecture to tell you to start talking about what quantum gravity is. So this function by itself, it doesn't have like necessarily, there is a small Q expansion. So this if you write it as a trace, like it has a series expansion in Q. So this itself is not divergent. There's no issue here. And if I write it like, yeah. So by this I mean like basically you can write it in terms of a series expansion, and this is a perfectly fine function. The thing that is happening is that now, the thing that is problematic is that the range of this sum is infinite. And you have to be careful with the convergence of like summing over the images. So what I'm doing here, I'm summing over all like the possible gammas acting on tau, roughly speaking. And that thing is the thing that is divergent. But like not each of the individual ones. It's like, it's that you keep on adding them on top of each other. And there's an infinite number of them that you're adding on top of each other. Yeah. Oh, so you have to check it. So that's the thing. So that's why I said here, the argument, like the quick argument, is that it is known that if you quantize the Virasoro group, you don't get higher loop corrections. It's a one loop exact quantization. And you can be like, sure, fine, Witten said so, therefore I believe it. But if you're stubborn, and actually nobody has done it, you can just check, someone should check it. Someone should just go and do a 2-loop or a 3-loop computation. And there's a paper that did it on flat space. And I complained to the authors, why didn't you not do it in AdS₃? So they did Minkowski-3, and they showed that in Minkowski-3, if you go up to 2 and 3 loops, the answer was 0. And in Minkowski-3, the algebra is the BMS3 algebra, and the BMS3 algebra is also supposed to be one loop exact. And so there's evidence from the BMS3, which is kind of weird, like from, yeah, but I think someone should like, should just go and do the 2 or 3 loop computation and show that those terms cancel. But yeah, but like the reason why people haven't done it is because you already know, like it's compatible with Virasoro. Virasoro is one loop exact, and so then they're like, It's like, yeah. But again, there might be a surprise. But yeah, but the expectation is that you should see that, like if you get something at higher loops, you should be able to just reabsorb it as a redefinition of what you meant by the central charge. That's the expectation. So it's not that, it might not be exactly 0, but it will just be like, oh, it's instead of 3L over 2G, it's 3L over 2G plus 1. And then, because you had to add a counter term, and maybe you had to renormalize something, and that's it. Yeah.
I have a similar question. I didn't always compute about the Lubin action. It can be written in the terms of the Lubin action. That will be kind of a classical action, has classical function that match with the function
But that's because you will have counter terms, that's all. From this point of view, it just means that the higher loop or orders will have divergences, and you have to add counter terms to fix it, and that will renormalize the central charge. Yeah. Okay, so we got that. What do we think? No, but again, you don't have to take y to be small or anything. I'm just illustrating how this is as a function of y, that's all. So the tau is a complex number, there will be x. So usually, so in the Maloney-Witten paper, they just write down tau as x plus I, y. And they're just, and so you can write it again like as a function, like, yeah, there will be real and imaginary parts of tau. Okay, again, like maybe tomorrow I'll just write to you the very illuminating like function that you get. I'm just trying to get some intuition of how this looks like. And the way that you get intuition on how functions looks like is that you expand them. That's all there's nothing deeper than this. That's all. But again, if you have great intuition on some very complicated Bessel functions, you can also just say, oh, of course, Bessel functions look like this. So, but I assume that that was not like your bread and butter, that you woke up every morning plotting Bessel functions. And so that's, yeah. So that's why I decided to like, oh, let me write it in this way so that we can see roughly what's going on with this answer. So if we did a good job or not, okay? I don't know, does it? I don't know. So I guess the question is, and it was the question that we were asking, does it look like a trace? Or if you want, does it look like a sum over energies where you have degenerate energies, and well, I guess here we have energies and angular momentum. Mm-hmm. It's an excellent question, but I'll tell you in a moment why not. We could have seen that from the previous lecture, that it was not a good Hilbert space interpretation. Or maybe, let me say it right, like, yeah, so, okay, but no, let me say it later. So when we try to fix the problem, let's get back, it's an excellent question that you're asking. Let me get it back as like when we try to think about what should we do next, okay? So, but yeah, so people. Is this true or not? What will be the first thing in what I wrote up here that will tell you yes or no to that answer? So maybe let me be a bit more clear in this notation. So as I was saying, tau, so this thing should basically look like a sum over some coefficients, where if I write it as Q, so this will be trying to think what is more useful for me to say. No, let me write it like this. Okay, so if I write it as trace of Q to the L0 plus Q to the L0 bar, and then this will be trace, so Q is e to the 2 pi ix plus iy times some eigenvalue, e to the 2 pi I x minus iy times some eigenvalue. So basically, my question is, does this look like a sum of decaying exponentials in y with positive coefficients in front of it? So maybe just focusing on the y dependence. So what I have here, I would have things that will look like right? Roughly speaking. No comments? So I'm basically, if this thing looks like a trace over a Hilbert space, it means that whatever function I get here, I should be able to decompose it in terms of exponentials of e to the minus 2 pi y and e to the 2 pi ix with the appropriate one, times positive coefficients here. What's that? Yeah. So what do you think? Exactly, thank you. So don't be like, so the answer is no. This thing here will not admit this expansion. Maybe you're not fully convinced by this, but the first reason is because you have this like inverse powers of y, and so you will not be able to resum it again in terms of decaying exponentials. But the most annoying thing, well, there's two annoying things. So there's this y dependence like this that comes out of the regulation. But then I thought that all of you were going to be like, what? It's a negative number. Traces over Hilbert space do not have negative degeneracies. And so there's actually, this is not the only negative contribution that shows up. It's the one that they noticed at first in the Maloney-Witten computation, but then there were, a few years later, a group in Caltech also noticed that there were other points in the expansion. If you expanded, so this was a small y expansion, but you can also expand in other regions of tau and tau bar. You don't have to necessarily take y small, and depending on where you expanded, you kept on finding in different parts negative coefficients. So this is negative, which means that it will not look like this. And the reason why I illustrated this part is because this is basically not compatible with having some type of expansion. They basically, if you look at the more carefully at what the functions are, you basically cannot write it as a sum of negative exponentials. And not even if you decided to have like negative exponentials, sorry, a sum over these exponentials with negative coefficients, it also still doesn't work. So you cannot even have it. So it has the problem that, so there's two problems with this computation. So and or maybe let me, people refer to this as a continuous spectrum, but basically you have a power series in tau instead of e to the 2 pi I tau. It's a function. This function will acquire negative values. Yeah, not all of the coefficients are negative, but some of them are. And so then therefore I can interpret the coefficients of this function as a degeneracy of states. That's because this thing here, this -6, is multiplying the eta function, and this eta function, it does have a Q expansion. So you would have said all the states that come with this eta here have like negative degeneracies. So yeah, we have a problem. So when we try to quantize this theory, we're not getting something that looks, to my mind, like really quantum in the quantum mechanics way. Okay. So what happened? In starting this discussion, we basically came up with some rules of how to compute the path integral. I implemented those rules and I got garbage. Okay, so what should we do? Okay, we can try to change the rules. Okay, so for instance, your suggestions. Like let's go through that first suggestion. So one possibility was don't put all the topologies, right? So you told me like you were too greedy, restrict the sum over topologies. So let's do exactly what you suggested, and we had like the answer. So let me just write it because it's roughly what we did in the last class. So let's say that we only include thermal AdS and BTZ because those were the two things that had a good Lorentzian interpretation. Robinson was also advocating for this. Okay, fine, let's do that. So what was the The answer here was C/12 times beta. I'll just do it for imaginary tau. You guys have to remind me about the signs here, but this basically went, sorry, this one was a plus, and I think this one was a minus, and there was some factors of pi, 3, 1 over beta squared, right? So that was the contribution from thermal AdS. This was the contribution from BTZ. And then you will have like the little corrections in it. This function, the corrections are not going to be important for what I'm going to say, but if you look at this, I have e to the beta. So this already, you would say, yeah, that looks like, yeah, you summed over a solution that had like e to the minus beta. But e to the minus 1 over beta squared is not of the form e to the minus beta. So how do you write this as e to the some energies times beta? I don't know how to. Right? So at least, okay, you can try to see like, oh, maybe if you remove some of them, it fixes this. Naively, for instance, if you just add these two geometries and all of its quantum corrections, sure, fine. You're not going to do all of this fancy like machinery of like, oh, there's all this complicated sums here. But it didn't solve my problem of having a trace because this exponential goes like 1 over beta squared. Or was it what? No, sorry, it was 1 over beta. The free energy went like 1 over beta squared, sorry. So it went like 1 over beta. So at least that restriction over topologies doesn't help. Now, some solutions to this, so in the literature, there's things that have been said. And usually, so there's the, okay, maybe let's weaken this. Let's not sum over all the topologies. Something that has been considered quite a lot is basically modifications to these two. So there's, if you add defects, then you get rid of the, so let me call this one problem A and this one problem B. So it cures B, sorry, it cures A. So you can actually add like basically singular solutions, and in particular, you only need to add a finite number of conical defects to get rid of like this -6. So you can add more solutions. And that at least removes the negativity, but B persists. And another thing that you can do is add off-shell configurations. They're not quite defects, because you could have said that defects are, in a sense, also a little bit off-shell. And this also does the same thing. It cures A, but it also doesn't cure B. Okay? So up to date now, nobody has been able to understand a modification of the gravitational path integral such that you fix both of these problems. Nobody has been able to fix this last problem. This last problem is, there's absolutely no clue how to get rid of this. Yeah, so the reason why, okay, so if you could have said, so another solution would have been, okay, just fix the topologies, but don't include the black holes, right? So from the point of view of this solution, as we said, this was already a perfectly fine Hilbert space, and then you forget about it. In a sense, that's something that you can do, but you will not describe black hole physics. Well, you will get this 1 over beta. So this part over here of the black hole will look okay, but yeah. So the problem is that if you want to have both of them at the same time, which seems like a reasonable thing to say, that you should be able to describe both configurations inside of the same Hilbert space, it just doesn't make sense. Okay, so it's a combination of the two of them. So each of them individually, you will be able to reinterpret it as a perfectly fine perturbative Hilbert space. Now, this Hilbert space, though, since some of you already know about AdS₃, this is not the Hilbert space of a conformal field theory. It will just be the Hilbert space of descendants of the vacuum. So it's not quite yet. It's not a CFT. It's only part of a CFT. But sorry, there were a few. I don't know where we should also start wrapping up. But yeah, there was questions like yeah.
Okay, what do you mean with adding defects?
So in the sum, you just add here the path integral that you would get around a defect at temperature tau and tau bar.
Defect in the geometry, or?
Yeah, so remember, so when we did the, so when I told you what were the smooth solutions, there was a thermal AdS there, and then here were the black holes. So in this sum, I'm basically including this, and I'm including the black holes. And so what people have noticed is that if you include some solutions that lie between here, and then do the path integral around those solutions, then that cures the problem.
Oh, thank you.
But only the negativity problem. The spectrum is still, like you still get this power series in tau.
Are there dimensional problems by having one exponential have beta, but the other one 1 over beta, since the central charge is C in both of them?
Sorry, if there's a problem with what?
In dimensions? But because
Beta is dimensionless in my conventions. So that's why it differed by a factor of L with the Hawking temperature.
Okay.
So yeah, I'm using tau doesn't have units in it, if you want.
Thank you. I have another question, but I don't understand the continuum spectrum problem. Yeah, that's it. I didn't understand the problem of the continuum spectrum. Can you tell me the overall idea? I don't need to understand the computations exactly.
It basically means, like by continuous spectrum, I mean that I can't decompose this as a sum of exponentials where their coefficients are integers.
Okay. But why did you say instead of the exponential of 2 pi tau? What does it mean to have a, that would be a discrete decomposition, right? If I had exponentials? Because it says power series in tau instead of exponential of.
Yeah, so this is a power series in
Yes.
tau. It's polynomials in y.
Yes.
But if I would have gotten here instead an expansion in exponentials in y, then that would have looked better, at least.
But why would that have been discrete?
No, but at least it would have taken me somewhere. So it's a combination of both. Yeah. If you insist on trying to do a decomposition in terms of these exponentials, the problem is that the coefficients here are not something, they're not going to be integers, they're going to be like kind of ill-defined, like they're going to look like weird functions. Like the density of states that you will infer is not something that is compatible with a discrete spectrum. That's all.
Thank you.
More questions? Thank you. You said that there are negative coefficients of different types, like doing this type of expansion with 1/y, you have that -6, but
Yeah,
if you
but then you can go to other regions of the complex plane and you're going to see, again, negative coefficients popping up. So it's not special to the small y expansion.
Okay.
It's just that historically that's where they found them first, but you can expand around other points and you will get, again, negative coefficients.
But in that sense, if you add those defects, you can cure like all different expansions at the same time?
Yeah.
Wow.
Yeah. But then it's a bit ad hoc because it's like, why would you add some defects? Like, it still doesn't cure the fact that the spectrum is continuous. So yeah, at least you got rid, like it's just an indication. So defects are usually understood as like adding matter. So if you add a point particle to the Einstein-Hilbert action, a point particle will induce a defect in the geometry. And so this is kind of like an indication. So what you're getting out of this, like the lesson, is that it feels like gravity coupled to matter might have the possibility of being a good quantum theory, but gravity by itself would not. So it's kind of, it's hinting towards that resolution. But then you would really have to do, I think the defects gives you that hint, but then what you really would have to do is say, no, let's now do the path integral with a field and try to do all this game again. Now, if you add matter, then it's much more difficult to quantify this phase space. So that's why it hasn't been done yet. So pure gravity, again, it has this luxury that I can quantify absolutely everything. But if you start adding degrees of freedom, then the computations start getting much, much more complicated.
Can't you add geometries that don't have boundary such that the boundary condition is still satisfied?
In a sense, yeah, that's also part of like this off-shell geometries, but like, yeah, you can also add singular metrics, like you can add something that has like no metric. Yeah, but again, if you start doing that, like the thing that people get nervous about is that if you start considering configurations, I'm not a huge fan of this route, because then I don't know what is the rule, like what are the off-shell configurations that I'm supposed to consider?
Okay.
Like it's not quite a satisfactory answer, and so there hasn't been, like, and again, when people add these off-shell solutions, they're motivated by JT gravity, by this 2D theory, but when they do this, again, it just cures A, but it still doesn't cure B. So it doesn't feel like yeah.
Is there a CFT picture of this problem of the continuum spectrum?
There is so there's a proposal on how to understand it. So yeah, I probably will not, I have just one more lecture left, and so most likely I won't have time to address it, but there's a proposal of like understanding that there's a way how you can like separate contributions in a CFT partition function such that this will look like the chaotic behavior of the CFT. I can tell you more offline because it requires like but yeah, there's some, nowadays like a lot of the work is trying to understand what do you have to do to the CFT, or like what classes of CFTs you would see that if you only focus on this part of the CFT spectrum without kind of looking at the rest, that makes it like a nice quantum theory. What would it be like that subsector of the CFT that kind of like tells you this is giving you this like fake continuous spectrum. But then the question is like from this point of view, it's like, what do you need to add to then complete it to something that it was good? And that's what's not clear. So most of the CFTs that we know don't have this. Well, all of the CFTs that I know do not have this property, but formally you can. No, that's another problem. So we haven't gotten there yet, but like, so there's different things that you can do from the point of view of the CFT. I'll try to discuss them tomorrow, like, kind of like what does the CFT teach us about like these obstructions, but you can just ask the question of like, how should you think about this part of the, like, is there a natural way how to decompose a CFT partition function such that it has a continuous part, and then, there's two more,
Is there a possibility restrict the Euclidean geometries to the ones have a well-defined Lorentzian interpretation or not?
Well, that's what we were trying to do there, and it still didn't do, it doesn't fix my problem. So these are the two geometries that had a good Lorentzian interpretation.
Okay, but it's not work.
No, because you have 1 over beta there, and 1 over beta is not something that you expand as e to the beta, right? Like, try to write this function as like a sum of e to the minus beta, that it's going to give you crap.
Small question on that as well. Even if you keep adding more stuff, that exact problem with that term, how would you?
No, but it's like, imagine like the eta function. So this is the magic of modular forms. The eta function is invariant under tau going to tau 1 over tau, right? But it's not like you see it term by term. So there exist modular functions that had this inversion symmetry, but the problem is that this is a very simple function that is invariant under beta going to 1 over beta. But yeah, didn't do the trick.
That's it?
Yeah, I guess so.
Okay.
Oh, sorry, and this was also a plus, so just.
We thank Ale again for time.